Hey, in this video I'm going to explain what the cyclotomic structure on topological Hochschild homology is. Cyclotomic structure on topological Hochschild homology for any ring, or more generally ring spectrum, is an additional structure. Precisely, it will be for every prime a map from THHR to THHR Tate CP. And this is a structure which does not exist for ordinary Hochschild homology and which is specific to topological Hochschild homology. And that leads later, as we will see, to the definition of TC and is the ultimate reason why THH is a better invariant than Hochschild homology. Hi, I'm Thomas Nikolaus from Mathematics Münster. Let's review the structure that we have already on topological Hochschild homology. So if R is a ring, or more generally a ring spectrum, then we have seen that topological Hochschild homology R carries an S1 action. So it's a spectrum with an action of S1. And as a result, we could define Tc minus R as the homotopy fixed points of that action, and Tpr as the Tate construction. Tate is 1. And this, of course, works in any symmetric monoidal infinity category. Category in place of spectra. Right, we've seen, I guess, in any, I should maybe sort of say stable and admits all colimits, then we can form Tc minus or Tp or the analogs Hc minus and Hp. For example, in the derived category of the integers, this came down to classical negative cyclic and periodic homology. And in order to proceed now, I want to introduce additional structure on THH that is only present in spectra. But to formulate that correctly, let me first abstractly tell you what kind of structure that is, and then we construct it concretely in the case of interest. Construction. Assume we have a fiber sequence of pointed, I guess, x, y, z, of pointed connected spaces. Connected spaces. And then, because every pointed connected space is the bar construction of a group object, we write this as BH to BG to BG mod H, where all of these are pointed connected group objects. And I mean, the point is that, I mean, every fiber sequence of pointed connected spaces takes this form. And of course, the reason I write it like this is, for example, if you had an ordinary group H sitting as a normal divisor in another ordinary group G, then we'd immediately get this kind of fiber sequence. BH, BG, BG mod H. So that's the examples we have in mind, and I guess in general it's just always, I mean, this is a definition. We just take a fiber sequence and that is G mod H is omega of that Z. Then there is a functor B G mod H into S, which sends a point to BH, which classifies BG. i.e., I mean, such a functor is just the same as a group action, so i.e. BH, H, G mod H acts on BH such that such that if I take the orbits for this action, so BH, and then the homotopy orbits for this G mod H action, that this is actually equivalent to BG. Right, and this functor which classifies just works for every fibration. Whenever you have a fibration, or like any map of spaces in fact, the infinity category of spaces being a fibration is not a sort of homotopy invariant condition. So you just have this map from Y to Z, then there's just a functor from Z into the infinity category of spaces, which for every point in Z assigns the fiber of that point, which, well, I guess for the chosen base point this is X, and then you have, like for every path in Z, you have a monodromy and so on and so forth. It's like the classification of fibrations. And in this case, it just specializes to the statement. And to see what's going on here, I mean, it's very interesting that for every such sequence, you have an action of G mod H on the classifying space BH. So there is a really good exercise which helps you understand what's going on here, and that is if H and G are finite and H is a normal divisor in G, then describe how G mod H acts on the classifying space BH. And as a hint, you should choose a section, a set theoretic section of the map from G to G mod H. And then let an element in G mod H act by conjugation on BH. And you will see, I mean, it's advantage to think of BH as a groupoid. Because in that case, I mean, it's a space or a Kant complex, but it's in fact a one groupoid, and then you can write down how this acts. You have to take into account coherence homotopies to do that. Well, that's a really good exercise to see what's going on here. But a consequence of this is consequence, or corollary, maybe, but let me say consequence because that was just a construction, is that for any infinity category C, we have that the functor category from BG into C is equivalent to the functor category from BH into C. And then I take the homotopy orbits for G mod H. Right, where G mod H acts on BH, and then, sorry, not the homotopy orbits, I misspoke, the homotopy fixed points here. Okay, and this is just a consequence because, well, I guess mapping out of a homotopy orbit, mapping out of a colimit is a limit. So strictly speaking, I guess we've argued in previous videos in our higher algebra series that on functor categories this also works. A priori this would only work on the groupoid core, so the mapping space, but with a little exponential law argument we've seen that this also holds for functor categories. So, and of course, I mean in general it's a very strong condition. You can't just take any group and decompose it in such a way. Having such a fiber sequence, I mean, you need to look at normal divisors if G is an ordinary group in order to get such decompositions. But here, of course, under this equivalence, I mean, if I project down to the functor category BH to C, then the composite from here to there is just a restriction. So what I'm saying is if I have an object with a G action and I restrict to a normal divisor, then I have a residual action of G mod H. And that residual action can be described a little bit more profoundly. As follows. So with some additional work, let me write that in brackets because I don't want to imply that this is completely obvious from everything we've said, but this implies that the functors homotopy fixed points H and Tate H, which are functors from fun BH C into C, right? C is any target category where those things make sense. Induce functors upper HH, upper Tate H from fun BGC, which is the same as fun BH, upper H, G mod H, as we've seen. And now I just want to say, well, here I have a functor into, maybe I'm running out of board space, into, now I go from fun point C, H, G mod H, which is the same as fun B, G mod H, C. i.e., and this is just, I mean, what I mean by additional work is what we need is the functoriality of limits and the Tate functor, as before, where we haven't really talked about that so much in this whole series of courses. But somehow what you do is you just take, I mean, you forget this thing and you just observe that this functor here is sufficiently functorial in the variable h, right? And because G mod h acts through maps, then this will follow. And the same is true for Tate, where somehow this relates to a higher algebra video of mine where I talk about this Tate construction. There I have just mentioned that Tate really is functorial in spaces. And that is what you use here. Okay, anyways, but the point is that for any, more informally, for any normal subgroup, H and G, if X has a G action, so an object action C has a G action, then XHH and XTateH have residual G mod H actions. And maybe one last thing I should say is such that, well, if I take the homotopy fixed points for H, and then I have this residual action, I take the homotopy fixed points for this guy, this is of course the same as just taking the homotopy fixed points for G to begin with. This is maybe for functor categories, this is clear, and in general this just follows by composing adjunctions, if you think it's true here. Like somehow the colimit, this functor is just adjoint to the inclusion functor, and so the last limit is as well adjoint. Okay, so that is what I wanted to say about residual actions. And I mean, if this whole discussion confuses you, the thing you have to take away is just the fact that in the case of ordinary groups, this is something which is maybe clear if I did that in a one category. I just took the fixed points for a group, for a subgroup, then there's an action of a remaining action of G mod H of the quotient, right? Because the H for which I've taken the fixed points acts trivially. Okay, and the example for which we'll need that is the following. So assume, I mean, so the G is T, like the circle group U1, and that is G, and the H I want to look at is in my case just CP. So this is the cyclic group of order P, cyclic group of order P, say P is a prime. I don't, for what I'm going to say now, it doesn't really matter that P is a prime, but later P will be a prime. So let's say it's the cyclic group of prime order and embedded at S roots of unity into S1. Okay, and then for an object X with an action by the circle group, we have that X upper HT and X upper HCP and X upper Tate CP have residual residual T mod CP actions. So this is really the quotient, but this is also a thing that's in the fiber sequence, if you think it's true. After classifying spaces, so they have these residual T mod CP, and what is T mod CP? We identify T mod CP will be identified with the circle group itself by, and what is the identification? It sends an element z, say in complex coordinates, to z to the p. Right? I think of this as a subset, I mean, circle group as a subset of the complex plane, and then just send z to the p, and that will just sort of, I mean, factor over this quotient and induce an equivalence. Okay, so that's a case of interest. Okay, now I can formalize the additional structure besides the S1 action that I want to formalize on topological Hochschild homology, and that's the following definition. A cyclotomic spectrum a cyclotomic structure. First I want to say what a cyclotomic structure is, and then a cyclotomic spectrum is a spectrum with a cyclotomic structure. On a spectrum X with S1 action, so it's a spectrum with S1 action, is given by maps phi p from X to X tate CP. That are T equivalent for every prime P. So here I mean X is by assumption a spectrum, and I guess I wanted to write T instead of this one. Sorry for that. So X is a spectrum with a T action, and then X to the tate CP is considered as a spectrum with a T action by means of this residual action. So here I really have an action by T mod CP and implicitly identify that with T again. That's very important, so implicitly identified here. Okay, and I have such a map phi p for every prime p. We refer to phi p as the cyclotomic Frobenius. Cyclotomic Frobenius operator or Frobenius map. Okay, so that's the first part. Second is that a cyclotomic spectrum is an S1 spectrum with S1 action, with T action, and cyclotomic structure. Okay, and that is the structure that we want to talk about today. And so the main theorem that we're going to indicate how to prove is the following, or the main fact is that for every ring spectrum R, THR admits a natural cyclotomic structure. Right. So we already, as I mentioned in the beginning, we already know that THHR, pretty much like Hochschild homology in every symmetric monoidal infinity category, admits an action by T. So the content is that for every prime P, we have a map. Maybe I write that. We have a map THHR into THHR, Tate CP. So we have such a cyclotomic Frobenius for every prime P, which is T equivalent. And maybe I should not always only say it is T equivalent, but of course it admits an equivariant refinement as such a equivariant structure is extra structure in infinity land as opposed to merely a property of a map. I want to make a few remarks here. So the first part is that the cyclotomic structure on THH is induced from the Tate diagonal. Or maybe I write like this, from the identity into this functor TPX on spectra. Well, this is a functor. The Tate diagonal was for every spectrum a natural map from X into the p-fold tensor power to the Tate CP. And so I'll explain in the rest of the video today, where I sort of indicate the proof of the theorem, I'll explain how the Tate diagonal the existence of the Tate diagonal of spectra can be leveraged in order to construct this structure, cyclotomic Frobenius. For the moment, let me just record that it is induced by that. And why do I record that? It does not, and by it I mean the cyclotomic structure, exist for HH R relative C, where C is an arbitrary stable symmetric monoidal infinity category. So that's a generality, or maybe, I mean, that at least a generality in which one can define Hochschild homology, and turns out that there's no version of the Tate diagonal in this generality. And this is maybe actually one of the reasons why, or let me first tell you where it doesn't work. One can, for example, prove that in the derived category of the integers, so a thing relevant to ordinary Hochschild homology, there is no map, no natural map like this. Tate CP. I mean, of course you can, I mean, in this case, this would be the tensor product over the integers, right? So I would just take P objects in the derived category and tensor it over the integers. This makes sense, and the Tate construction also makes sense in the derived category, but the point is that there's no map from here to there. One can actually check that every such natural map has to be pointwise the zero map. And if I sort of ask it to be lag symmetric monoidal, which the Tate diagonal is, then there's just no such map. And therefore, HH of any ring relative to Z does not admit any sort of cyclotomic structure. And I guess one can also directly obstruct the existence of a cyclotomic structure on Hochschild homology. One doesn't have to go through the Tate diagonal and the construction. And so there we see that this Tate diagonal that we have in spectra, which goes from every spectrum into a thing where I tensor over the sphere, this is a very important piece of structure, and we have produced a video in our higher algebra theories where we talk about this map. And Achim has explained how this induces a sort of Frobenius. And so as a result, we see there's no version of that Frobenius for the derived category of the integers. But of course, I mean, this is a straight generalization of the classical Frobenius from abelian groups or classical rings. And so you see, for this purposes of talking about the Frobenius endomorphism or Frobenius maps, the category of spectra is actually the correct generalization of the category of abelian groups and not the derived category of C. Okay, these are the remarks that I wanted to make, and for the rest of the video I will just go about constructing this cyclotomic structure. For those of you who just want to take this for granted, believe that there's such a structure, and maybe it's good to remember that it has to do something with the cyclotomic, with the Tate diagonal, that it's basically induced by the Tate diagonal. Right, and I want to give you two constructions of the cyclotomic structure on THH, and the first construction for R and E infinity ring. I mean, this will be anyways the most important case of interest, for example, an ordinary commutative ring. So in this case, it turns out it's a little easier to understand the cyclotomic structure than in the case of an arbitrary E1 ring. So, but in order to do this, I'll need some auxiliary tool, namely induction. So let me talk about induction of G objects. So C is an infinity category. With all colimits, all small colimits. And this is not necessary for everything, but I'm sure you can work out which colimits are actually needed. We will actually mostly apply this to spectra and commutative algebras in spectra, so there's no harm in assuming this. Then we have a forgetful functor for any group G. And of course, group always means group object in the infinity category of spaces. C to the BG down to C. So the thing, just forgetting the G action. And so what is induction? Induction is the left adjoint to this functor. Proposition is this functor has a left adjoint given by the functor which sends a C in C gets mapped to the colimit over G, not over BG, but over G of the constant functor C. And I guess we would have written this as C tensor G earlier, with G action on G. So this is again, as before, this is functorially in G. So G is just considered as a space here without any additional structure, and then you have a left action of G on this G, and then as a result you can act on the whole thing. So that's a statement that this is the general form of induction. And the proof, with some parts which are not completely rigorous, is, well, I guess we just have to check the universal property, right? We just have to construct adjunctions pointwise, and so we just check the universal property for this specific guy. So we just check that what are maps in C to the BG from this colimit C tensor G. Let me write this suggestive notation. D, well, this is just same as I guess that's a statement about how mapping spaces in C to the BG look like. Well, the claim is these are just mapping spaces in C from C to G of the underlying, and then there's a conjugation action, right? Whenever I have two G objects, I can conjugate act on the mapping space, and the statement is that this mapping space is the homotopy fixed points of that mapping space. So that's a statement about mapping spaces in CBG that I'm using. Just actually, once you contemplate how to make the statement and all the terms are rigorous, not hard to prove. Basically by using a bar construction definition. And here now, of course, this is the same as the mapping space from G. That's the mapping space in the infinity category of spaces, map C, comma D. So that's basically just the universal property of this colimit. And then, of course, upper HG. And here now, how does G act? Well, G first acts on this G, but then it also acts on the D. But then by usual shearing isomorphism, this is as a G object equivalent to the thing where I just act on this guy. So that as a result, the whole limit is actually just the mapping space in C. So these two guys cancel out from C to D. Okay, and that actually proves the claim. And of course, again, I've used a bunch of identifications, which I don't want to make completely rigorous, but that's the idea. Okay, so that is the induction. And the induction is just super general. It just works for every infinity category with colimits. So what is a classical example? Let's say, I mean, we have C being the infinity category of space, spectra, and G finite. Then, of course, we have that the direct sum over G and G of an object C is the free. Right, free meaning it just satisfies this universal property. So the left adjoint to the forgetful functor is taking the free G object, and that is just the direct sum here. And the same, of course, in the derived category of the integers. So if you, or like say, even in the one category of abelian groups, if you just want to form for any given abelian group the free G object on that, you just take the direct sum over G's. So it just recovers these formulas. And for G equals the circle group, it is even a little bit more funny. Then, and again, C is spectra, then we have that the free T object is, I guess, C tensor T, right? And this is the additive tensor, so this is actually because T is just S1. S1 has as a spectrum just two cells, a 0 cell and a 1 cell. Decomposes, so this is just C plus a shifted copy of C. Well, that's maybe a little bit more mysterious, but I mean, it's also not so mysterious if you think about the two cells of the S1 as a spectrum, like the point and the 1 cell. But anyway, so maybe it takes some time to get used to these homotopy theoretic actions here. But the case we will care about is the following example. And that is C is the category of commutative ring spectra. Right, that's completely legit as a category. I mean, it has all colimits. And let's say if G is finite, what is then the free object with an action? then this colimit, and let's say we have any ring spectrum, R is a commutative algebra in spectra, then how does the colimit over the elements of G of the diagram constant R look like? Well, this is just a discrete set, so this column is just a coproduct. But a coproduct in commutative algebras, as I've explained in one of my higher algebra videos, is just a tensor product. So what you get is that this is just a tensor product, where you just have G many factors. Right? For every group element, maybe there would be a better way to index that. I have just this tensor product with permutation G action. Right? So in this case, and so because this is more, I mean, this is like R to the tensor G. That's why in this commutative algebra situation, I'm not using the tensor G notation, but I write upper tensor G. For example, if the group is a group with P elements, a cyclic group, then we would just write R to the tensor P. And there you see that this is literally, by this abstract formula, this is the induced object. So the induced object with the G action, but through commutative algebra maps. And okay, so in the additive case, I've talked about the case of a finite group and the S1, the circle action. And now in the multiplicative case, the finite case just works the same. You just replace direct sums by tensor products. But the S1 case there is different. So what is it? So the statement is for R in commutative algebras in spectra, we have that R into THHR exhibits THHR as a free E-infinity ring with S1 action under R. Proof. By our general formula, the free object is given by the colimit over S1 of the constant functor R. And I guess previously we had written that R to the tensor is 1. We have seen that this colimit is THHR. In lecture 9. So lecture 9 of this course about topological cyclic homology, and this is around minute 14. So I've at least claimed that and said a few words of why this is true. So you see that already here, like, this is kind of mysterious, right? You just tensor up, you just form the free thing with S1 action, and all of a sudden you get THH. Well, that's the universal property of THH. And I guess this just gives me a S1 action on THHR such that it's free. The fact that this S1 action agrees with the previously constructed S1 action on THH through cyclic objects. Well, I mean, let me say I skipped this. So I acknowledge the fact that there's something to be proven here, and I don't. Let me just indicate in words how this is done. So what you do is you go through the construction of the S1 action on THHR, which is through cyclic objects. And you observe that in the E infinity case, the whole cyclic object is actually a cyclic object in the category of commutative algebras. And once you do that, you see that this is literally, then the action is literally just somehow under the equivalence of THH being this colimit, this is just literally the S1 action on the simplicial object given by S1. So yeah, I guess I'm just saying that it can be proven, and I don't think my comments now are of any real help, but there is a claim that this S1 action agrees with the other one. Okay, so good. And now I want to use this fact, the universal property of THHR, to give it a cyclotomic structure. And so construction. For every R, commutative ring spectrum, we have the map from R into THHR. Right, the inclusion into a colimit. This is a map of E infinity rings. Okay, that map will play a role. I mean, this is a triviality. I'm just recording that here. I guess by the construction of the lag symmetric nodal structure on THH, this is a map of commutative algebras. And we form the target has an S1 action, T action. In particular, we get an induced CP action. Right, but just restricting along the inclusion from CP into T, considered as roots of unity. Thus, we get a unique extension to a CP equivalent map, or map of objects with CP action, from the free thing with CP action on R, which is just R tensor ... R, P times, into THHR. So this is a map of E infinity rings with CP action, where here I act by permutation, and here I act with CP on THHR by restriction of the S1 action. And of course, if you think through what this map does and how the construction works, and this is maybe also a really good exercise to understand how much you could follow what I did today. So as an exercise, I ask you to check that this map as a map of spectra is also just given by, I mean, this is a colimit over a cyclic bar construction by the inclusion of the P's term in the cyclic bar construction into THHR. Okay, but I mean, this construction gives me more, namely it tells me that this is a map of E infinity rings. I guess you can also check that, but sort of specifically also gives me the claim that this is a CP equivalent map. Okay, so that is this map. CP equivalent map. And also, that's the second piece of structure I will use in a second. So in particular, I mean, what I can do is I can also like get a map on Tate constructions, right? Tensor R Tate CP into THH R Tate CP. And the last piece of structure was that we had the Tate diagonal. Tate diagonal is a map from R, I guess for any spectrum, but in particular for R, into R Tate CP of commutative algebras in spectra. And so the way we, if you don't know what the Tate diagonal is, we have produced an additional video on the Tate diagonal in our higher algebra series. Roughly speaking, the Tate diagonal informally sends an element of R, whatever element means, to just the tensor product R tensor dot 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 R. Consider it as an object in the Tate construction. The point is that the Tate construction is a lag symmetric monoidal functor. So this whole thing is a lag symmetric monoidal functor, and the Tate diagonal was a lag symmetric monoidal transformation. As a result, if we apply it to an E-infinity algebra, then this is again an E-infinity map. That uses Dunn additivity. Infinity plus 1 is infinity. Or infinity minus 1 is infinity, actually. And so this is a map of commutative algebras in spectra. And now I will use these three maps in order to construct the cyclotomic structure. So as a result, maybe let me state that as a proposition. There is a unique T-equivalent map of E-infinity rings. So R is going to be an E-infinity ring throughout. Then THHR is an E-infinity ring. It has an action through E-infinity maps. And then the Tate construction, Tate CP, again is an E-infinity ring. And of course we have this residual action again, where on this guy we have T mod CP, which implicitly, as before, we identify with T. So the T-equivalent map of E-infinity rings fitting into the following diagram. So that's my VP, my cyclotomic structure. And what is the diagram? Well, I guess I have this bottom cell inclusion, R into THH, R, the first map over there. And here now I have my Tate diagonal, R tensor dot 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 R Tate CP. And then I also have this induced map here, THHR, Tate CP. So that's the second map I've constructed here. And now the claim is that there's a unique such map here. Right. So this is the Tate diagonal. And why is this true? Well, this is just the universal property of THHR. So we do have this E-infinity map from here to there. And the target carries an action of S1, right? I mean, really S1 mod CP identified with S1. So as a result, we get a unique extension of this map over THHR, because this was the free E-infinity ring with S1 action, as we've just shown. So this is just immediate from what we've done. And that is the cyclotomic spectrum on THHR, and this makes the spectrum THHR, at least for an E-infinity ring, into a cyclotomic spectrum. I mean, it makes it into a little bit more than a cyclotomic spectrum. It also, at the same time, is a commutative algebra, and the two structures interact in the sense that the cyclotomic Frobenius is a map of E-infinity rings. So that's maybe a cyclotomic ring spectrum or commutative cyclotomic ring spectrum. And let me end this lecture by saying a few words as to what to do in the case of associative algebras. So the case of R being an associative ring spectrum or E1 ring spectrum. And I will not entirely give you the construction, but let's first recall that THHR was by definition the colimit column over delta op of the cyclic bar construction, which was just R to the tensor n. N in delta op, and then I have R to the tensor n. And let me write this cyclic bar construction just as THHR bullet. Maybe put the bullet below. Okay, and then here is just bullet and delta. Okay, and really, this is not merely a simplicial object, but a cyclic object. So where THH R bullet is actually a functor from the cyclic category into spectra. Right, okay, so so informally, we can write this as follows. So R, then we have R tensor R. These two maps here, R tensor R, and I guess I now realize that I should have probably written n plus 1 here, because it starts with 0. And so on and so forth. And what happens actually, a cyclic object, the way I think about a cyclic object is that this carries an action by C2, this carries an action by C3, and so on. And the action, of course, is just given by permuting the factors cyclically. Okay, so that is the cyclic object THHR bullet. And what we will do is we will construct the cyclotomic structure as a map into another cyclic object. Namely, what we're going to do is we're going to say that there's another cyclic object which here has R tensor P, Tate CP. And then here you just do the same for R tensor R. So you have R tensor 2P, Tate CP. So you think of this as just taking this as an atomic unit. I mean, like, by what I just mean, like, replace in this construction R by R tensor R. That's how the action goes. And then here I have R tensor 3 P Tate CP. And so on and so forth. And so the claim is, and this is maybe what, I mean, you would call this a p-fold HY subdivision of THHR Tate CP, would be maybe an appropriate, very lovely name for this object, just for the experts. And so the claim is that this is also a cyclic object. And so what we're going to do is the cyclotomic structure on THHR arises from a map of cyclic objects as above. So what I'm claiming is here, you know, here I have the Tate diagonal, delta P. Right, and here what I want to do is I want to put the Tate diagonal, also the Tate diagonal, but apply it to the spectrum R tensor R. And then again here I have the Tate diagonal, but now apply it to the spectrum R tensor R tensor R. right? And the main complication comes from the complications from the way of viewing the target as a cyclic object. And why is that? Well, I guess I don't want to really go into that, but just, I mean, if you just sort of saw my video now, and now you nodded all the way that everything sounds believable, then you should somehow just try to write down, I mean, without any coherences, without any fanciness, what the phase degeneracy and action maps here are. So this is a really good exercise, so I recommend writing all these down. And actually, because Tate is rather mysterious, so I recommend doing that, replacing Tate by fixed points and by working just in abelian groups. Just let all these be abelian groups and just take the actual fixed points as opposed to homotopy fixed points. And then I recommend like trying to think through how this object possibly is a cyclic object. Because you have to be a little bit careful that certain things you could write down agree and don't agree. So just maybe go through the first few layers. That's a really good exercise at this point. Okay. Anyways, once you realize that the target is a cyclic object, so there's some sort of intermediate, in order to make that precise, there's some intermediate category lambda p involved, which is the p-fold cover of the category lambda. It's also a quotient of the category lambda infinity. At the moment you've done that, it comes down to some functoriality behavior of the construction delta p. Okay, so let me not, neither do any of these. So I'd be very happy to go through the combinatorics. This is basically a really nice exercise in combinatorics. So if any one of you guys wants to see that exercise spelled out, please drop a comment and tell me. Maybe I can produce a short additional video explaining that. But until then, let me just take that for granted. And now, now what does this get us? So as a result, we get a map of spectra with T action from the THHR, which is just the co-limit over delta op of THHR bullet, into the co-limit over delta op of this object, which I lovely called SDP THHR TCP. And now, of course, this is maybe just, right, which is just co-limit delta op, and then I had just R to the delta Pn TCP, n. I guess I should write Pn plus 1 again, n in delta. And then, of course, I have this interchange map, which goes from this co-limit into the thing where I pull the Tate out. So it goes to the co-limit n in delta op, R tensor P n plus 1. Just take a co-limit like this and pull the Tate construction outside. And then you see that here I form the co-limit over the thing where I just multiply this by P. And that is actually what is called the edgewise subdivision of a simplicial object. So, and it turns out this has the same co-limit. So this is literally THHR TCP. Okay, and from the fact that this was a map of cyclic object, we get that this is actually a map of spectra with T action. and that is the cyclotomic structure in the associative case. So except for me skipping over all details of the combinatorics, this is how you get a cyclotomic structure for THH of an E1 ring spectrum. And note there's no ring structure anymore on THH. So the cyclotomic structure is everything that you have for THH of an E1 ring spectrum, as opposed to the case of an E-infinity ring where THH still was also an E-infinity ring. Okay, that finishes my video for today. In the next video, we are going to explain how this cyclotomic structure can be used to define topological cyclic homology. Stay tuned for that, and thanks very much for watching.